The question is, what do we do if we have a particular formalism that doesn't have these properties? So the underlying idea of this talk is then sometimes we can just change the rules of the game. So whenever I talk here about cheating in this talk, I don't want you to think about something mean, but something innocuous. Something like, think about a professor who says, I don't want to teach Paxos. Let's just see what happens and run with it. And the same is this here. If you have something that doesn't fulfill certain properties we love and we like, we can switch a little bit things so that we have everything we want to have back. Yeah, so cheating is something in this case not mean, not harmful. So the overall focus, our overall focus with a very general problem, semi-supervised node classification. We assume we have given a network with a couple of labeled nodes. And now what we want to do is we want to assign the appropriate type, label, color to all the remaining uncolored nodes. So we assume there's something, some unobserved references going on. So certain kind of nodes prefer other nodes higher than so different types of nodes. So for example, if you look at this one, you may see that the green nodes like to hang out amongst themselves, but the orange ones like more the blue ones, and vice versa. And the way you can think about this is, let's just calculate, so let's just count the number of edges of a certain type. And if you do this, you will see, well, amongst the orange nodes, you will see about, yeah, exactly, there are 12 different types that point to a blue node. So when you can think about this is, and the way I want you to think about this is some kind of affinities, preferences, some probability distributions, compatibilities, frequency tables. So, for example, amongst the so if you look at the orange ones, let's see if this works. So amongst the orange ones, you see that, well, 60% of the orange edges, outgoing edges, they point to blue ones. So now in real problems, you also often have node attributes. For the purpose of this point, this talk, we assume there are no node attributes. So we only look at the relational information, the graph structure, no attributes. And then there are two variants of the problem we're going to study. The first one, given the network, given the seed nodes, and given the known compatibilities, how can we label all the remaining nodes? And in second time, we then relax this and say, we don't have the compatibilities. We don't know. We only observe the network. Now we want to learn first these compatibilities, and then we use it with some method to label the remaining nodes. So these are the two problems we're going to study. Okay, so let's do this in turn. The first one, so where do we start? We start with an algorithm that's widely known in probabilistic graphic models, belief propagation. At its core, it's a dynamic programming algorithm that works on a tree-based graphical model. And for reasons that we have seen already several times in this workshop, Fokion's idea about local to global consistency. We have seen Nico's dynamic programming algorithm. So what is the idea? The idea of this algorithm intuitively is, and why we like trees is because every node is connected to every other node with exactly one path. So if S sends a message to T, then S is basically the root of the subtree of all the other nodes from that direction. So the algorithm proceeds in the following way. It accumulates all of the messages from the neighbors, then adds its own beliefs, and then prepares a message to be sent from S to T. And the interesting thing is now that the message gets modulated with the potential. So for example, if you're green, then we are giving the highest frequency to other green nodes. As you can think about these compatibilities as a probability distribution. Yeah. Now here's the exact formalism. We don't need to pass this, but that's the intuition. So the node accumulates all of the messages. It multiplies the messages. It multiplies it with its own belief. And then it modulates, transforms them over all of the possible states it has, and then sends the message. And then this whole thing gets sent around until hopefully things converge, guaranteed to converge, like a semi-joint reduction in acyclic schemas. But real-world problems are, in the graph-based world, usually not acyclic. And we've seen if we have now cycles, then things do not work very well. So what do people do? People cheat. So people cheat and say, actually, let's just run these algorithms on graphs with cycles. That's also called loops. So it's called loopy belief propagation. So people run this on graphs with loops. And surprisingly, it works quite well when it works. But it doesn't always work. And it's a long literature where people have basically observed it works really well. However, sometimes it does not work. If we have certain loops, it's really complicated to make this algorithm work. So the idea, if you're already cheating, if you're already using an algorithm that is not actually made for loops, why do you don't cheat in the appropriate way? So,
when it doesn't work, you mean that it doesn't converge, isn't it?
Correct, it doesn't converge. Lopez?
Straight to page ranking.
Actually, excellent. I will show. The basic idea is what we're going to do. We're going to flip this. So we're going to change this. We're going to cheat a little bit in a more informed way. And then we get some formalism that turns out to generalize PageRank in a very nice way.
Perhaps does exist a tree cover of the graph that work well, so this could be the basis that we can apply the computation.
So I think what you say is the formula is if you have a graph, if you have a cyclic graph, you just look for a spanning tree.
Yeah.
But imagine like you have a really dense graph. Everybody is connected to 100 friends. You have a very dense one. Then assume the number of edges that you have. Is it really reflective? Because very often you want to also have triangles, which everybody is excited about in this workshop. So we want not of throw away the edges and the connections. We want to leverage this, but we don't want to run into these problems. We want to have some nicer properties. Maybe we want to have something like that we learned from Javier, who was here. Yes, do things converge? Can we have some fixed point? So that's what we did. So how do we cheat? We linearize. We linearize the equations of PageRank. Because then we change it into some algebraic convenient form. It turns out, based on Flora's question, that this is a very nice intuitive generalization of PageRank to something that's called heterophily. Homophily means people of same orientation like to cluster itself, green nodes, important pages linked to other important pages. Here, maybe opposites attract. Yeah? So if you look at biological networks and you want to substitute a particular a protein, you may want to substitute with something that has the same function. These two may not actually interact with each other, but they have the same friends, but they're not friends themselves. And it turns out in the more modern language, what you get is like an infinitely deep graph neural networks that has no nonlinearities. This goes back to Boris, but let's see if it works out fine. Okay, so what we're doing? Let me 2 pages. What we're doing is, so basically we're looking at all of these different variables that I've shown you. The compatibilities, the beliefs, the messages, these are the 3 things that get sent around in this formalism. And then we identify some uninformative point. So if I give you this matrix, compatibilities, you don't learn much. I'm orange, well, 1/3, 1/3 that you're orange, blue, or green. And the same with probability distributions and with the messages. So here one is a bit more careful. And then we look at the difference, at the residual, and then we formalize the whole equation system in terms of these residuals. And then we're going to use Taylor expansions. So Maclaurin series, we look at the particular things that are happening in the equations, and we approximate them. So the nice things happen. Here's the intuition of what's happening behind this. Is the original formalism multiplies the different messages. Yeah, so you get here 0.5. When we need to normalize, and it turns out that normalization is one of the complicated things that make PageRank so complicated. If you change it, we have a different normalization constant. That's the key thing. What we're looking into is actually at the residuals, and then we replace multiplication with addition, and intuitively what we get gives us the same flavor, right? So 69% or 70%, but the prediction is still the same. The first class wins. But now we have a very nice equation system that has addition, so the multiplication, and everything is normalized by design. So what we get, and this goes back to Flores' question, is actually a very nice intuitive update equation. So what we have is any possible Breyer beliefs. Those are the nodes which are already labeled. We have the adjacency matrix. F is the beliefs we want to have at the end, and F is this compatibility matrix. Now, to Flores' question is, if you now compare this with PageRank, that's pretty much the same. Yeah, the difference is that we don't have the column normalized matrix, but just the matrix itself. That's also called cut centrality in social network analysis, and a little bit other things. But now what we have is we can investigate these equation systems with the tool that we also heard from Javier. And it turns out we can say, actually, we can give a closed form solution. And we can study when these equations actually converge. So, and intuitively, exactly if here, this expression has a spectral radius smaller than 1. This means the biggest eigenvalue is smaller than 1. And the intuition behind this, let me just remind you about the example we saw from Javier. I think you used the A's for this, right? 1 plus A plus x squared, geometric series. And we know exactly when it converges. So if you have 1/2, it converges. Minus 1/2, if you have 2, it does not converge because the spectral radius equivalent, the absolute value, is bigger than 1. And that's actually this is intuitively the same what we see here. Yeah, 1 is the identity matrix, and here we have a conical product between two matrices. Yes.
Normalize to make the radius less than 1?
Yes, exactly. So that's what we do basically. So we're doing cheatings. So if something does not have this the spectral radius we want, we just tone it down a little bit, just barely, that we just don't run into the non-convergence issues. So that's exactly what we do. So what we lose in experimental results, not much. I have here a backup slide, just in case. So this means, so actually, if one compares with belief propagation and belief propagation, in certain assumptions, in certain situations, one does not lose too much. But the best things are still to come. And then one more thing is also because Joe has shown us some example code, belief propagation is quite nasty to implement. And we have seen that if you change something in different formalisms, you can just express something in very few lines of code. How many lines of code do we need for linearized belief propagation? Just one. Yeah, so today you can do as a PyTorch, this was just NumPy, but you see exactly these updated equations, right? So dot product, you have a sparse representation with NumPy, and that's what you have. So it's really just one line of code. And let me know the big picture, the best is yet to come. So what is the overall picture here? So if you look at probabilistic inference is hard. So the model, and from inference in practice, we have to approximate it. Now, if you want to learn a model, we normally have to use the same algorithm that we perform in inference on training data. So this means if the inference is hard, the learning is also hard. Because learning normally uses inference as a subroutine, into cross-entropy, backpropagation, gradient descent approximations. So I assume that Guy, and from the second workshop we had, people would say, does this really make sense, right? But we've learned from the whole ideas from compilation, why do we compile knowledge into a model that is complicated to work with? So can we actually, because inference is hard and learning is hard, can we just replace this? Yeah, that's the idea. So we replace it with a model that we prefer because out of algebraic convenience. So, and the interesting thing is then now we have some very easy inference because of the properties, but the best is actually we can also make learning fast. Yeah, and to use also an expression from Joe, crazy fast. So I promise you this stuff is going to be really, really fast. Yeah. So I'll show you how fast this is. So, so here is how long does it take to propagate information to perform inference? Unsurprisingly, it's linear in the number of edges. The bigger network, you send more for the network, how well does it work if you have fewer labeled data points? Also unsurprising, if you have fewer and fewer labeled data, then the propagation gets more and more diminished and is not as accurate. Yeah? So here, for example, we have just 10 labeled nodes in a graph of 10,000 nodes. So 1 per mil of labeled nodes. If we use the standard textbook approach, we need more time to learn the parameters because we use inference as a subroutine. And at the same time, we also get a drop in accuracy. Because if we have some holdout set, we need to fit the data. We have fewer data to fit, and we also have to bypropagate this. So what I'm going to show you, in contrast, is faster inference. So actually, in a fraction of the time we need to propagate from inference, we can learn the parameters, and it's also as accurate as if we had the original data points. We have just 10 data points in a graph. We learn the compatibilities and we propagate them. We get the same thing as if we had known them from the beginning. So what is the trick? So the idea is that we separate learning into 2 steps. So we want to learn these compatibilities, but we first create some efficient representations of the graph. Think about this factorized graph representations. We perform some statistics that are very small and compact, and then we perform the learning on these more compact representations. And the first part is actually just linear in the size of the graph, but the second part, the optimization, which may take more time, is done just in the size of these representations. So it's really, really fast. Okay. Any more questions? Yes, okay.
I was wondering at the picture that you have some slide before, where is the red arrow that are the complicated approach to compute the solution, the green one that are the easy one. No? Mm-hmm. One of the questions that sometimes we have on machine learning is why the model gives this explanation. And there are some approach line, some tree classification, and so on, in order to explain why the model with this difficult methodology inside give this result. I'm wondering if you use the green arrow, let's say a more easy way to compute the solution, give also an easy and more human, intelligible and explainable way to
Yeah, so most definitely, I think quite excellent. This I think goes also back to Zach's talk, and then I think Boris' question. So if we have everything linear, then we're back in the semi-ring framework, and everything we know very well how this works. These people by line, people try to have something complicated, approximate it, linearize it amongst the point, and then try to give intuitive explanation. So I agree with it. Yeah. I agree with it.
But you're linear, right? You don't have activation function.
Correct. We linearize it.
Why did you mention graph neural networks?
Oh, I will come to this at my discussion slide. So so the question is, should I jump to the discussion, or should I still show you what we actually do? I think I have, 10 minutes, quite good. Okay, so here's what we would like to do, but it doesn't work, and then we're gonna tweak it a little bit so that it works, yeah? So here's the thing is, if we have a fully labeled graph, then we can do exactly what I showed in the beginning, we just do counting. We just count the number of edges of pairs of different colors, and we can then normalize this, and then we are done. Now, what happens if we have a sparsely labeled graph? The issue is if we have, what we could do is we could still just look at the neighbors. Here we have just 2 neighbors. We calculate the statistics, and then we still want to normalize it and find the closest doubly stochastic symmetric matrix under some distance function. The problem with this is that if you have a sparsely labeled graph, so I assume I give you 10% labeled nodes, what is the fraction of edges we have labeled on both sides? So with 10% independently chosen, then 10% times 10% is 1%. So we just have 1%. So if this goes down, we get fewer and fewer data points from which we get. This is the idea, yeah? A quick detailed slide of how this could be done, yeah? So in the spirit, you can calculate in a sparse framework just with one pass over the data, the label types of nodes of different color. You can normalize it so that the rows sum up to 1. And then you have a simple optimization problem under L2 norm to find and fit the closest substochastic symmetric matrix. But this doesn't work if we have very few labeled nodes. So what is the idea? But the idea is that we now look at just further distances. So think about one particular node, an orange node. Orange, this means the entry, and this is orange. What do we expect about its neighbors? If it has out degree 2, well, that's basically this entry of the matrix we want to learn. And as we go further and further away, the strength of the signal gets diminished, but we have an exponential number of neighbors of a certain distance. Yeah? So this gets weaker and weaker, but we get more and more information, and we're more likely to have more neighbors. That's the idea. That's basically all what there is to it. And the nice thing about this is now we have actually here, with the distance, we can recover the very few labeled nodes.
This is a local computation, because you only see your neighbor. This can be made also in a distributed fashion, or not?
So can one do it in a distributed fashion? I assume, because everything just it's like a linear algebra expression which needs to be compiled. The distance, we go up to distance 5. If you have like a graph that has a diameter of 5, then everybody's connected to everybody. And we somehow want to calculate this efficiently. And I will come to about how we calculate this efficiently in a moment. And basically the idea is now we do something very similar to what I showed you before. Yeah. So we create an energy function where we get the statistics from different length paths, and then we try to we just look for the closest one, the closest matrix H that fits all of these different statistics we get for paths of different length 1, 2, 3, 4, 5. In this case, we go further down, we get better results. So that's fine, but there's two things actually that are still not correct. The first thing what I just told you is actually not working, because if that's what we want, and we do, and we see actually we get a biased estimator. Why do we get a biased estimator? Because look, what's happening is, if I tell you that every node has an out degree 2, then a distance 2 path is actually back to the node. So this means we get a biased estimator because the most frequent label of a node of distance 2 is itself. So we need to be a bit more careful and only look at what's called non-backtracking paths. So be more careful about what we calculate. Only those paths which don't directly backtrack over any of the distances that we calculate. The second thing is, and this goes back to Stefano's question about a graph, if we now want to calculate all of the, so if W is a sparse matrix, yeah, big, but everybody's connected to a constant number of neighbors. Now, if we calculate the matrix to the powers of higher up and higher up, we quickly get a dense matrix. So n to the power of 2. But now we can use all our beloved algebraic properties. The basic ideas of rational I, it's basically an aggregate query. It's an aggregate query that we can factorize in a way to calculate very efficiently. So we can calculate 10 to the power 14 path in a few milliseconds. And the idea for this is exactly what this workshop is about. So if I give you, for example, here a relational algebra expression, then we know that we can push the projection behind the join. The same we can do also with this linear algebra expressions. If I tell you that this is here a sparse matrix, you want to calculate this expression. This is here a thin label matrix. In a few minutes, what do? We apply the law of associativity. Why? Because then we're guaranteed that our intermediate results, this is a common topic that we've seen throughout this program. We want to calculate something. The outcome is very small, right? We want to have a 3 times 3 matrix. We don't want to calculate intermediate result sizes that are big. So how do we do this? Well, we keep them small by having the right approach of how to factorize them. So it's exactly the same idea of FAQ. We need to be more careful about because of this non-backtracking path, but the idea is exactly this idea that's seen throughout this workshop, that If you do it in the right way, you can calculate very efficiently. Yeah. So, like the FAQ framework, generalized distributivity law. I think tomorrow, Janine is also talking about what Jeremy Kepner and him is doing with associative arrays. Okay, so discussion. Question that Flores said, how does it relate to graph neural networks? So I've used this here. This is a slide many of you have seen who looked at graph neural networks. It's from the lectures nights from Joel Leskovich. It's also something that Zach had in this neural network. So you want to calculate something about this graph neural networks. Think about unwind this into something also Stefano, like a tree-based, yeah. And then in each of these different boxes, you have some neural network that does something, yeah. And the basic idea of this graph convolutional networks was that you have here some neural networks, and at the end, you fit this with cross entropy. There was some work that's called, let's simplify this. A simplified graph convolution says, well, you know what? We don't actually need to have here nonlinearities. We just keep this linear, and we just have one nonlinearity at the end, the softmax function at the end to fit the data that we have. And it seems to work as well. So we came from a different part, from belief propagation, and said, can we simplify it? But if one now looks at what it actually is, you could say this is nothing this else, because we have now exact guarantees about when it converges. It's like a graph neural network with infinite layers. And we are guaranteed to avoid over-smoothing because we know exactly the convergence guarantees. So that's for open topics, last slide. So one thing is, there's a lot of focus in, actually most of the papers in graph neural networks. So one lesson is, the more data you draw at a problem, the better you can fit. So if you now compare this with approaches that use also node attributes, it won't be as good. But how much do we learn? I think one question by itself that is not completely clear is actually, how well can we learn information from a given network without attributes? Because attributes, there's so many assumptions. Attributes, you use some outside learned the large language models, but then you bring out information from something else. How much information is actually available in a given graph without the attributes? I think this is something that's worth to study. And then basically what kind of effects you can have that make the linear methods, so suppose that you're losing something, but actually how much do you lose in practice, really? If you have like a phenomenon that is just based on just preferences from neighbors. Are there higher effects that cannot be as well represented? And then basically, yeah, what are then the appropriate architectures that can learn just based on the graph, no attributes, assuming certain effects? Okay, with this, thank you.
Time for one question. Right, well, there will be questions after the session for discussion after the next talk. So a well-deserved break.